Hello everyone. Today I'm going to give a brief introduction to this paper, Quasi-Monte Carlo Features for Kernel Approximation. So kernel method is a mathematically well-founded and practically powerful modeling framework. It is remarkably effective in small and medium-sized problems with certain optimal statistical results. However, it may become infeasible for large-scale problems due to its time and memory requirements. For example, the kernel ridge regression is computationally intensive when the number of data points is large. It has space complexity n squared and time complexity n cubed. There are various approximation techniques, and in this paper we will focus on random features, which is based on Monte Carlo method, and it is well understood theoretically. Our goal in this paper is to further improve random features with Quasi-Monte Carlo method in place of the Monte Carlo method. So we first provide some preliminary of the random features approach. It is based on the fact that many kernels have an integral representation as follows, with pi being a probability measure over some space omega and psi a function. For example, for any shift invariant kernel, the Buckner's theorem implies that the kernel is the Fourier transform of a measure mu, and by some algebraic transformation, it can be written in such an integral representation form. More specifically, the shift invariant kernels cover many popular kernels in machine learning, such as the Gaussian kernel, where mu is the Gaussian measure, the Laplacian kernel, where mu is the Cauchy distribution, and the Cauchy kernel, where the mu is the Laplace distribution. So given the kernel function has such an integral representation, the kernel can be naturally approximated by replacing the integral by a finite sum with omega 1 to omega m IID from pi. So here we are using the Monte Carlo method. Using this approximation reduces the complexity of the kernel ridge regression to that of the usual ridge regression because now Km is an inner product on Rm. By central limit theorem, the approximation error is 1 over square root of m in probability. There are some limitations here. So first, the error bound is non-deterministic, it is in probability. And second, the error rate 1 over square root of m decays slowly. So in this paper, our goal is to replace the Monte Carlo sequence by a quasi-Monte Carlo sequence to yield a deterministic error bound at the rate 1 over m up to logarithmic factors. So Quasi-Monte Carlo method is a powerful tool in numerical integration. It focuses on approximating the integral over the unit cube with a finite sum for some well-chosen deterministic sequence that are spread out more uniformly in some sense. For example, here we plot the first 25 points of the two-dimensional Horton sequence. So we can see that it seems to be more uniform compared with the IID random points on the right. So QMC targets functions with finite variation. The classical Cox-Marloka inequality states that if f is a function with finite variation, then the error in approximating the integral can be controlled by the variation of f multiplied by the star discrepancy of the points used for numerical integration. And for Horton sequence, which is a QMC sequence, the star discrepancy decays at the rate 1 over m up to logarithmic factors. So a natural question is like, can we directly apply the previous inequality when approximating the kernel in the random features approach? So a negative result was found by Avron, which states that for all shift invariant kernels, the integral representation from the Buckner's theorem has infinite variation. So the classical inequality cannot be applied. So our contribution in this paper is that we show that for a class of shift invariant kernels, including Gaussian kernel, even though the integrand has infinite variation, the singularity is mild, so the approximation error can still be well controlled by 1 over m up to logarithmic factors. So now we will first state our results for shift-invariant kernels. So we assume that the mu from the Bochner's theorem is a probability measure with independent components, with the ith component having cumulative distribution function phi I, and later we will need some conditions on these phi i's. By a change of variable, we can write the integral representation as an integral over the unit cube, and we denote by omega the variable to be integrated. So in our QMC features, we will set omega 1 to omega m as the first m points in the Horton sequence instead of MIID points. And we define the approximated kernel as what we did in the classical random features approach. So in order to achieve the 1 over m error bound, we need some condition to characterize the situation where the singularity is mild. So our condition is on the marginal CDF phi I, and we assume that the derivative of the inverse CDF at t can be controlled by a constant divided by minimum t, 1 minus t, for all t between 0 and 1, and also the space of X is compact. It can be shown that the Gaussian kernel and Cauchy kernel over a compact domain satisfies this condition. And these two kernels are examples of universal kernels. That is, the associated function class can approximate any continuous function arbitrarily well. So this fact makes them particularly useful for machine learning applications, such as kernel ridge regression. So if the previous QMC condition holds, then we can show that the approximation error of the QMC features is 1 over m up to logarithmic factor. And the proof is based on the fact that, first, the singularity near the boundary of the unit cube is mild when the previous condition holds. And second, the Horton sequence used here avoids the boundary of the unit cube. So our QMC features can also be applied to non-shift invariant kernels. But note that for non-shift invariant kernels, the Bochner's theorem is no longer applicable. So whether the kernel has an integral representation over the unit cube needs to be considered on a case-by-case basis. So if the kernel has such an integral representation form, and the integrand is of bounded variation controlled by a constant C0, then we can simply apply the classical Cox-Marloka inequality to yield an approximated bound 1 over m up to logarithmic factors. There are a number of non-shift invariant kernels which satisfy the previous condition so that the 1 over m error bound holds. For example, the mean kernel, the Brownian bridge kernel, the iterative kernel, the natural cubic spline kernel, and the product kernels of any previous kernels, which allows us to construct high-dimensional kernels. So for all these examples of kernel, we can still apply QMC features and have the 1 over n error bounds. So finally, we will state the application in the kernel ridge regression. So recall that in the exact kernel ridge regression, we have space complexity n squared and time complexity n cubed. With the random features approach and our QMC features, the space complexity is n times m, and the time complexity is nm squared plus m cubed, and m is the number of features being used. A natural question is how large m should be. A short answer is that our QMC features require a smaller m compared with the classical random features. In order to achieve the same error rate as the exact kernel ridge regression, the classical random features require m of order n to the power of 2r over 2r plus 1, and our QMC features only require m of order n to the power of 1 over 2r plus 1, where r between a half and 1 is a smoothness parameter of the regression function. So we will have substantial improvement in smoother cases where R is large. In order to more formally state our result, we introduce some notations. So we let H be the reproducing kernel Hilbert space, which is the space consisting of the function consisting of the linear span of kx dot and their limits. And we define the integral operator as follows. There's a fact that the range of L1/2 is the reproducing kernel Hilbert space. We make the assumption that the true regression function of the kernel ridge regression is in the range of Lr for some r between 1/2 and 1. So r may be viewed as a parameter of smoothness. Under some standard conditions, such as the continuity of the kernel and the Bernstein conditions on the response y, we can show that when the regularization parameter is optimally chosen, then m of order n to the power of r1 over 2r plus 1 is enough to guarantee that the SS risk is of the same order as the exact kernel ridge regression, and this m is smaller than that required for the classical random features. So here's a brief summary of the paper. So our goal is to have a faster approximation of the kernel methods using Quasi-Monte Carlo methods instead of the Monte Carlo method. The main methodology is to replace the Monte Carlo sequence in the random features approach by a Quasi-Monte Carlo sequence. And we will have theoretical guarantee, that is, with m features, the approximation error can be improved from 1 over square root of m to 1 over m up to logarithmic factors for a class of kernels, including the Gaussian kernels. So that is the end of the presentation. Thank you for your listening.